A student of Ashish and Mohammed and Ali. So this is how we have been thinking about algorithms for the last many decades. So we have data, and that's consumed by an algorithm, and that produces an output. And this algorithm is supposed to compute some function that we are interested in. And in fact, this falls into the classical setting of algorithms, where you assume the data is fixed or is stationary, so it doesn't change at all. And the algorithm has unrestricted access to the data. Say in the PRAM model, you can access any location the data and then make some computations. Then you produce the output. But over the last few years, we have slowly realized that this model is not sufficient for many real-world problems. And that has led to a huge collection of more contemporary models of computation. I'll just list a few here, just to give you a flavor of what kind of directions people have been looking at. So one is online algorithms. There you have the algorithm sitting there, and input data arrives one by one. But the key restriction here is that the algorithm, once it makes a decision on an input, it cannot revoke its decision. So the decisions are irrevocable. So as soon as it sees the next data item, it makes a decision whether to say update a data structure or do some computations, and then after that, it has no choice but to live with that. That's online algorithms. And more recently, there's a family of algorithms called streaming algorithms, where the restriction on the algorithm is on the amount of space it uses. So the data is so big that no algorithm has the capacity to store all of it in memory and then do the processing. So not like the traditional model. Therefore, an ideal way such an algorithm would operate would be to take the data and then say, for example, compute a succinct sketch or a succinct representation of it, and then perform computations on that. That forms streaming algorithms. And if you trade space for time, you get what are called sublinear algorithms, where again, you have the entire, for example, the graph sitting, and you don't have time to explore the entire graph. Instead, you should spend sublinear amount of time, sublinear in the input size, to query the graph and perform some computations. And finally, in a completely different line of thinking, we also have algorithmic game theory, where you actually the algorithm actually influences how the system behaves. So that's a completely different line of thought. So the point here is that while most of us have been happy with working with a classical model of computation, the modern data needs, which we'll see in the next slide, dictates us to think about some other ways of data or the computation itself. In fact, many of these things, the previous models I put up, are motivated by evolving data. So you can think of data as a snapshot of nature, but the nature changes slowly over time. It changes, but the changes are sort of slow. And the requirement we have is that we need to keep up with such changes by constantly observing the nature and adjusting the solution based on new observations. So that's data, for example, think of the data being like the position of all the stars in the galaxy. They do, of course, change, but the algorithm has to do some computations on these positions. It has to do that by keeping up with such changes, by trying to probe or trying to query the nature and trying to get some data from that. Of course, this is not feasible computationally because it may not even be possible to track all the changes, because changes can happen without notifying the algorithm. That's the first thing. And second is, changes can occur anywhere. No, we're not in a position where we can try to observe or predict where changes will occur. So it can occur anywhere in the system. So we have no way of doing it efficiently. And finally, as we'll see in some applications, we are not really interested in the changes per se. What we really care about is some particular function we want to compute. And as long as the function we want to compute has some guarantees of correctness or goodness, then we are happy. So we don't want to track each and every change that occurs in the system. So we only care about what it does to our problem of interest. That's the motivation. And here are actually concrete examples. So let's take web pages. Of course, all of us know there are like billions of web pages. And even now, tens or even hundreds of millions of hyperlinks, links between web pages, change on a daily basis, right? So imagine a search engine company. The natural question is, which portions of the web should I focus such that I have to crawl that portion on a daily basis to keep up with as many changes as possible? Say, for example, to compute PageRank. That's a natural question. So I don't know where changes are going to occur, but somehow when the search engine tries to crawl fresh content from the web, it has to focus on the right aspect. Otherwise, it'll end up being stale. Right? So here's another example from social networks. Once again, on a daily basis, friendships are formed and broken. Right? So millions of links are modified each day. So, and suppose I don't work for Twitter, but I want to track all the friendships on Twitter. As a third-party person, which users should I focus on who do the changes most, such that maybe I can compute some global reputation, like say PageRank? Right? So, of course, I can't go and get the data from Twitter en masse, but instead, if I use my resources available in a judicious manner, then I'll be able to make the best use of what changes exist there. And this scenario is not unique to either web or social networks. It occurs in pretty much every network, communication patterns or traffic networks and so on. In fact, it even occurs in like settings like public opinion, right? I mean, everybody has some opinion about a topic, and of course, these opinions keep changing all the time, and there's no way to track all these changes simultaneously. The only thing we can do is ask a few people what they think about the topic. So these are some motivating examples of why we need to look at evolving data. So I couldn't come up with a better name, but I want to call this like the evolving nature of algorithms. So what I want to convey in this talk is actually not more about the algorithms per se, but here is a slightly new model of computation that we can start playing with. So once again, the data here changes slowly over time, and the goal we have is to compute some function of data at each point in time. So I'll give you a more concrete example in the next couple of slides. So what is the power of the algorithm? The algorithm actually can query the data at a few points. It has the ability to query. It can query the data and try to find out what is the latest value in that position. Of course, the algorithm does not know where the data is changing. So this seems completely, the algorithm has no hope of doing anything because the data can change adversarially, right? But if we put some restrictions on how the data changes, and if we give some more power to what the algorithm can output, for example, we don't expect the exact answer, maybe an approximate answer or a randomized solution, then we can show that we can do a bunch of stuff. So this model actually we studied in a work a few years ago for some like scalar problems like sorting and so on. And then we extended this model to some couple of graph problems like connectivity and minimum spanning tree. And then more recently, we looked at PageRank in this model, and then I'll try to present the PageRank thing here. Okay. So here is a formal description of the model. So the data arrives over a period of time, and let xt be the true data at time t. And our goal is to compute some function f on this xt to produce a value, say, yt. And we assume that the input changes slowly. The input changes can be stochastic or maybe even adversarial, but we don't know any examples for that. The only requirement is that the successive changes between two timestamps is small. So d is some distance. And of course, I've stated this in the most general terms. So x can be a graph, x can be a number, or x can be a matrix or whatever. So the d you see here will actually depend on the domain that you're working with. But the restriction is that the distance function is actually small. So you're not talking about huge changes that occur every time. And it's not a big restriction because you can make time as small as you want. And what is the power of the algorithm? The algorithm can make limited probes into the data at a particular time. So think of the algorithm and nature operating in tandem. So at each step, the nature makes a change. The algorithm has the ability to make one probe. Yeah.
So you have complete oracle access to the data.
Yeah.
You can query anything.
Yeah, you can query anything. Yeah. The only question is the only interesting thing is that what things to query. Right.
Limited probes means like something in the vicinity of where the change has happened, something like that.
No. It's completely, you can probe. Limited means the number.
Okay.
So right now we just look at one change per time step. So, but we can trade off the rate of change of the data versus the probing rate of the algorithm. So
But you don't actually know what changes.
No, no.
That's,
So the algorithm is completely oblivious to the changes happening. And of course, I mean, you have to keep in mind that if the problem is set up such that changes are adversarial, then no algorithm can do anything because you're giving too much power to the changes. So they have to be the right balance so that you can make some interesting statements.
Sorry, one more. So fundamentally, you need the fact that f is sort of continuous with xt, right? With x. That is,
Yeah.
if x changes a little, then f should not change too much as well.
Yeah, exactly. Some kind of a Lipschitz property.
Yes,
Yeah. So okay, so the algorithm maintains probes the data, and then it's allowed to do whatever. I mean, we don't restrict on its space or time usage, so it can maintain a complete snapshot of what it thinks the data is, and then its only goal is to output some solution y prime of t, and which should look like yt. I mean, this looks a way too powerful model, right? Because how is it even possible to do guarantee such a thing? Okay, any other questions about the model?
So just quickly, as you just said, you can do, you may not want to, but you could do exponential amount of work as long as you're not doing too many probes.
Exactly, yeah. So the only question is what information I care about. Okay, so the model I stated was in more general terms, but for graphs, here is what we look at. So we look at unweighted directed graphs, and let G sub t be the graph at time t. So we assume a few things again for analysis and simplicity purposes. We assume the node set does not change, so V is fixed. There are no new nodes are added or deleted. And we also assume that the number of edges does not change. We assume that the edge set size is fixed, but of course edges could appear or disappear. So we use E to denote the size of the edge set. And the assumption of data not changing too much translates to this thing. We assume that treated whatever way, network or matrix or whatever, E sub t plus 1 minus E sub t is small. So the changes is limited. And as I said before, it's not a big deal because you can choose t to be very small. And we don't particularly assign any specific change model. I mean, the change model will really depend on, if the change model again is like too general, we can't do much. So whatever results we get will depend on the change model. And what about the algorithm? So at time t, the algorithm can probe any node u and get its current set of neighbors. And it actually should be n sub t of u. So all the edges in E sub t of the form u comma v. So you can just get the neighborhood of a given node. So this is the exact setup.
so is there an assumption that at some point you see the full graph?
No. It's continuous.
So you never know the full graph.
No.
You're just observing.
Yeah. In fact, there is no full graph, right? So it just keeps changing.
Right.
Yeah.
Did you know E0?
Oh yeah, we assume that initially. I mean, again for simplicity, we can assume we know G0, but
Okay.
it's not really needed because
That was my question.
yeah. So you can assume that you start off with the same graph. Yeah.
Okay.
So okay. So this is the model. Okay. So as Seshadri pointed out, the only question here is what should be the probing strategy? How should I probe the nodes? In what order, or who should be the next guy to probe? And that really depends on two things. First of all, what is the change model? Like, how do I assume that edges changes between time shots? And then, what is the actual goal? What is the function I want to compute? Okay. So here is a more concrete example. So, as Jennifer is pointing out, the assumption here is that the algorithm starts off with a graph that it knows to be correct. So G1 be the graph. So algorithm's view of the world is the same. But the world changes, so this edge disappears and a new edge arrives. But the algorithm, for some reasons, chooses to query this node, so it doesn't see the change. And in the next time step, this edge disappeared and a new edge arrived. But at this time step, the algorithm was lucky enough to query the green node, so it gets the previous update from the previous time step, and so on. In the next step, there's a bidirectional edge just shows here. And the algorithm is lucky enough to get the blue edge and add the edge. So this is maybe at a particular time, and here is what the algorithm thinks the graph is, and here is what the graph is actually, right? So somehow it doesn't know anything more, but it has to compute some function. But what ordering should the probing be done? That's the question. Okay, so I'll give two concrete examples of this paradigm. The first is ST connectivity. So here the problem is you're given two specific nodes S and T in the graph, and you want to maintain a path from S to T to specified nodes. And here is a change model. So you assume that the edges at T plus 1 is obtained in the following way. You pick a random edge from the current graph, and pick a random non-edge from the current graph, and then you swap them. So basically take out an existing edge and put in an edge where one didn't exist before. And this is because you want to pick a random non-edge because we assume for simplicity that the graph size doesn't change, the number of edges. So just to make that. So a couple of things. To make the problem interesting and non-trivial, we have to assume two things. First of all, we need to assume that the number of edges is at least n log n. Otherwise, you won't even hit connectivity. And number of edges is not too big, like not more than n root n. Because if the number of edges is too big, then basically everybody has a common neighbor. So the interesting regime is where the number of edges is between these two things. So as I said before, the model is like each node gets a neighbor. Okay, and here's the algorithm. So think of this algorithm as proceeding independently. Okay, the graph evolves one at each time, but the algorithm doesn't even look at the graph. I mean, doesn't even pay attention to the progression of the graph, but just these things, does this in parallel. So first it tries to grow a ball, Bs, around the source node S of roughly square root of n over log n visited nodes, where by visited I mean the following thing. You take, in your current ball, you take a visited node, pick the closest unvisited node, and then probe that node and add all its neighbors as into this current ball. And that's my ball growing algorithm. And similarly, it grows another ball Bt around T of similar size. So you can show that under these graph growth assumptions, that roughly these two balls of like size square root n, right? So in expectation, they should have actually a common neighbor. And therefore, you can expect that the intersection of these balls is non-empty. And therefore, I can just use that non-empty intersection to construct a path from S to T and output it. So that's what it does. So the algorithm just proceeds like this. And so, of course, in steps where, remember the algorithm is supposed to output a path at every step, right? So you can assume that it will output the last path it knows about. So the only question is, how do I make sure that it's not like way too off, right? And that's not actually too difficult. You can show that the probability that the generated path is invalid, over the time steps is something like 1 over square root n log n. And that occurs because of the way we assume the graph grows. If you think about it, the graph is more like a GNM graph. And as time progresses, it's more like a random graph of degree, out degree, total number of edges to be exactly n. So using such properties, you can actually show that the path output at every step is not too bad. In fact, actually, you can improve upon this. So the idea is, instead of maintaining one path between S and T, you allow for some fault tolerance. You try to maintain two disjoint ST paths. And it's like the power of two choices. You can show that there's a significant improvement in the error probability. You can show that the generated path is invalid with probability at most like log n over n. And one can ask, like, maybe I can try to maintain like k paths, but you can also show a lower bound that any algorithm is of this form, like the probing algorithm, has to have an error of this something like log n over n log squared n. So it's basically tight. So you can't hope to improve much upon these things. Yeah. I mean, so the point I want to make here is that this ST connectivity is an interesting problem, but if you choose the model carefully, then you can do some things non-trivial with that. Okay, so let me switch to my second example, which is PageRank. So you have no choice but to see another definition of PageRank. So let me go through it quickly. So we know that PageRank pi is a stationary distribution of the random walk. So with probability 1 minus epsilon, you pick one of the neighbors at random and then go to the neighbor. And with the remaining probability, go to a uniform node. So assume that teleportation is uniform. And the stationary is the PageRank. So it can be written in this matrix vector form. And I don't need to motivate PageRank again, like Ashish and David did a wonderful job with that. So it's well motivated. And what's the goal here? The goal is to compute PageRank on an evolving graph. So the graph keeps changing, and I need to output a vector pi such that it's pretty close to the truth. And one natural notion of what truth is, of course, the algorithm outputs pi prime, and we look at the maximum error between these two vectors, like how much each coordinate deviates from. So the L infinity norm of pi prime and pi. And you can also look at the L1 norm, and we insist that I should be able to bound how much how much I'm off from the truth. That's good. And the way these algorithms, or even the previous algorithm, worked is that they don't do anything fancy in terms of working with a graph. They just maintain a view of what they think is a truth, and they work with that graph. So in fact, even this algorithm will do the same thing. It will maintain a view G prime of what it thinks the truth G at time t is, and it will compute pi prime as a page rank of G prime, and then output that as a solution. Okay, so that's the goal. And what can we do here? I mean, what is the what is the flexibility and freedom we have here? The key observation is that a high PageRank node has more effect on the PageRank of other nodes. So in fact, some of these things are actually motivated by Ashish's work with Barman on the PageRank, updating PageRank faster. So if you look at this equation, pi of u is proportional to pi of v over degree. And therefore, if at time t this value is large and v is changing, v adds or deletes a node, then it will have a huge impact on pi of u. Therefore, nodes with high PageRank are the candidates to query. Right? That's the natural intuition there. Remember that, but we don't have access to pi t. That's what makes it tricky. We only have access to pi prime or prime of t. We never have access to the truth. We only have access to the approximation. But if you assume truth is like approximation at time t, then this leap from pi to pi prime may not be a bad one. So that naturally leads to the following algorithm. We call it the proportional probing. So here's the idea. Pretend that pi prime looks like pi. Okay. And then at time t, you pick a node v to probe with probability proportional to pi prime at the previous time step. And then of course update your view of the world with this new query and its neighbors. And then compute PageRank on this new graph, maybe using Ashish's fast algorithm, and then move on to the next step. Right? So the question is this a good thing to do? Right? So a quick detour. So this algorithm is probabilistic, but actually you can make it deterministic by a standard trick. So this leads to a slightly better algorithm we call priority probing. So you can think of it like a deterministic version of the previous algorithm. So initially everybody has 0 priority. Okay? And at time t, so maintain a heap. At time t, pick the node with the highest priority. So let v be the node with the highest priority. You probe v and obtain all its neighbors. And output g prime and t and so on. And output a page rank. And then you reset the node's priority to 0. And increment priority of everybody else by the pi prime. Right? So sort of like v has been probed, so it sort of goes down in the queue, and then everybody else increases proportional to what their page rank values are.
Is it the neighbors or all the nodes?
Which one?
The priority of
Everybody, all the nodes, yeah, everybody, yeah. So, so what you can show is that this deterministic scheme still picks each node with the right measure. Not only that, but you won't have the bad effects of randomization. You're also guaranteed that every node v is picked at least once in like order of 1 over its page rank steps. So you won't have no unlucky instances here. So it will never miss a probing a set of nodes because of randomness. So just a small detour. Anyway, so what about analysis? So again, like we have to be careful with what the change model we assume to be able to prove some things. So here's the change model we assume. So at each time t, you pick an edge uniformly at random from the graph, and then you want to reorientate that edge. And the way we do that is you pick a node w with probability proportional to its PageRank in the true graph, and then redirect UV to UW. So basically, if a node has high PageRank, it has a higher chance of getting a new edge. So basically, rich get richer sort of thing. Again, this you might argue with why this is the right model, but this is a model where you can actually show something interesting. You can show that in the steady state, the actually it should be PaGERANK, sorry. The approximated PageRank vector is given the truth at time t-1 and my version of truth is very close to the actual truth of the PageRank. Yeah.
So your algorithm is more general, right? Suppose you had a system of linear equations and the coefficients were changing over time. Are you effectively just maintaining a solution, approximate solution?
Sort of, though I don't know how to.
Change model.
Yeah, it might work out, but I don't know. So that's a good point. Yeah. So this is a guarantee you can maintain. So you can show that the solution you compute is not far from the truth, even though you never see the truth. Okay. So in fact, I don't want to bore you with any experiments. I didn't show any graphs and so on, but they're all there in the paper. But you can see. So this algorithm actually does pretty well. We tried on some like large graphs, including maybe even some subset of Twitter maybe. It does pretty well actually, because the changes that happen in real world graph are not too far away from this actually. They're not really adversarial. They are random in some sense, may not be in this sense, but they are sort of random. So, all right. And the proof of this actually uses the random walk interpretation from Ashish and Berman's paper. So, okay. So I want to conclude my talks with a few things. So I hope I convinced you that evolving graphs actually is an interesting model. It's worth looking at, even some basic problems. And the question is, can we obtain like more interesting algorithms for like maybe more non-trivial problems on such a model? For example, clustering coefficient, or betweenness and centralities, things that are studied very much in social network literature, and also community defining and clustering. So, thanks.